second here. You're live.
Well, good evening, everyone. My name is Alyssa Hagan.
And I'm Michael Rozeski.
And tonight we are really proud to present to you Liftoff, which is a study of how vortex generation over wing foils affects the lift and drag as seen on the wing itself. So before we get into the meat and potatoes of our presentation, I'd like to kind of overview what you're going to hear from us tonight. First and foremost, we're going to give a high-level project overview, give you a little bit of background and content before we start throwing everything at you. Next, we'll overview our personal interest in this study, some of the environmental implications, as well as the applied fluid mechanics principles. Next, you'll really see us get into the details of our presentation as we overview our assembly and our manufacturing based off of our wing design. Lastly, you'll start to see our setup and testing with a data review and lots of graphs. The graphs are the most interesting part, I will say. And we'll give you a review of our findings and explain some next steps that we'd really like to take with this project. So, first and foremost, this entire project is built off of the fundamentals of lift and drag. Lift and drag and pressure over the wings are core to how airplanes fly. I'll get into one of my pet peeves about how people have used Bernoulli to identify how a wing should fly or how a plane should fly in a moment. But basically, lift is generated as there is a pressure difference across the the top and the bottom surface. On the bottom surface of a wing, you have a high pressure. On the top, you have a low pressure, and thus you get an upward force due to the pressure imbalance. So a wing does not span indefinitely. Thus, at the wingtips, you actually have a mixture of the high pressure and the low pressure zones, which creates these vortices. Ultimately, these vortices are generated because of lift. You cannot have lift without having some type of induced drag. It's simply not possible. However, we wanted to understand how you could potentially mitigate the effect of the induced drag on the overall efficiency of the wing. So, as you can see on this project, it kind of shows that fluid mixing with the vortices trailing off of the wings. So, our personal connection. I have been building and designing RC airplanes since I was a sophomore in high school. It's one of my biggest passions. It's truly fun to get to take this thing that just existed in your mind and ultimately see it flying in the sky. I also work at General Motors, and I was an energy engineer. So as an energy engineer, I was responsible for certifying the fuel economy of our up-and-coming EVs. So aero was absolutely crucial in how we were running our tests. And ultimately, being able to have this study and have a better understanding of vortex generation specifically felt like a very solid application to my career at GM.
And so my personal connection wasn't as direct as Alyssa's, but I've always been fascinated by different types and the depth of engineering that goes into building planes, as long as the principles behind everything. And so that's where my main connection comes from, but as well as I've always been just fascinated by planes since a young kid, going to air shows with my family. So that's why we decided on this project.
And one of the things that we both enjoyed about this project was getting to apply the path of fluids that we've been working so diligently to compound in our brains throughout the course of this term. So recently we took a trip to Toronto, and as we were walking through the streets of Toronto, dressed up in very formal gear, we happened to come across a hallway that was called the path. And we just felt it was so suiting for our presentation. And immediately we looked at each other and we were like, it's the path, we have to have it. So getting back to a little bit more serious content here, the environmental impact. Of course, this study, as everyone has kind of touched on in their presentation so far, the implications of drag on efficiency and ultimately fuel economy is very, very important. So like I mentioned earlier, induced drag is always going to be present whenever there is lift. So it is truly an optimization problem to make the handoff of how much lift do you need, how much do you want, and how much is the induced drag as a result of that. Of course, like everyone has kind of touched on so far before, reducing drag automatically reduces the minimum amount of energy that is needed to propel a body through a fluid. Then in hand with that, we have the engineering optimization, like I just touched on. And lastly, one of the things to keep in mind when we're going through our presentation is scale. So our wing form is relatively small. You obviously see a lot larger wing form, whether it's my RC airplanes that I'm working on all the time, if it's in personal flyers, and obviously once we look at jets and commercial flyers. So these little tiny minute differences in lift and drag that we see in the tunnel have massive implications once you start scaling these things up. Okay, now to talk about some of the fluid principles that we were using in this project. Manometry, day one, most important thing that we learned. We use manometry in our wind tunnel in order to calculate not only the static stagnation pressure in the wind tunnel, but ultimately to determine our fluid velocity of the air flowing through the wind tunnel. We used a pitot tube, which goes hand in hand with the manometry. It's a stagnation static tap. And we used Bernoulli to calculate our air velocity in the tunnel. And I'll touch a little bit more on Bernoulli in a second once I get to my biggest pet peeve about airfoils and lift. Then we use pressure taps in the wings themselves in order to calculate the static pressures as we have like the different streamlines going over our geometry. We use the concept of the Reynolds number to kind of narrow down what our expected coefficients of lift and drag, or kind of our desired, would be for the wind tunnel. And again, I'll touch on this in more detail. And lastly, lift and drag was kind of the main focus of this. We wanted to see the variation in lift and drag between our two wing designs, and especially we wanted to focus on that pressure difference because of the wing, between the just base wing form and the wing with the winglet. So, my biggest pet peeve when it comes to lift.
Can't wait for this.
So, we're all familiar with the principles of Bernoulli and streamlines going over like different surfaces. We spent the last couple weeks kind of reviewing this. So there's a theory called the equal time transit theory. And this is like one of the biggest fallacies. So when you look at an airfoil, when you look at an airfoil, imagine that you have the streamlines going around it. So the equal time transit theory tried to justify the increase in velocity and change in pressure over the top and the bottom of the wing by saying that the particles moving along the streamlines had to meet at the trailing edge at the same time. So of course, like looking at this geometry, you say, oh, the distance to go from here to here is a lot bigger than the distance to go from here to here. So there must be some type of change in the pressure as a result of that. This theory is very false. There is nothing that dictates that the particles have to move along the different streamlines and meet at the trailing edge at the same time. And moreover, it completely disregards one of the core principles of Bernoulli, which is you have to look along one streamline that simultaneously looks along two streamlines and makes a lot of assumptions that are not false. So, thank you for listening to my mini rant. It is just something that really annoys me. But, jumping into a little bit of wing design 101. So, the anatomy of an airfoil and some of the language that you're going to be hearing throughout our presentation, the most critical things to take away are the angle of attack and then the chord line. And so when we look at the actual airfoil that we selected, we decided to go with a symmetric airfoil. A symmetric airfoil is significant because when you have it at zero angle of attack, there is no lift generated from that. So the lift that's being generated from a symmetric airfoil is due to that angle of attack. So the specific airfoil that we selected was the NACA 0012. There's a database with a bunch of airfoil data plots and all the dimensions of it and lift and drag plots like I'll show you in a second. And we estimated that our Reynolds number based on the velocities of the wind tunnel would be between 400,000 and 800,000, which means that we're in turbulent flow. So this is a screenshot from the NACA website. And this is the plots that I'm pulling from in order to show you the data of what we would kind of expect for our lift and drag coefficients of the airfoils. So again, since I mentioned that we were going to be between that 400,000 and 800,000 Reynolds number, these are the curves that we would expect to see. So ultimately, we settled on a 5-degree angle of attack, bringing us to a coefficient of lift versus alpha of about 0.5, and a coefficient of lift versus drag. Well, actually, this plot's just kind of cool. It just shows you the lift versus drag. And then once we look back again at the coefficient of drag versus our alpha, we'd expect to see under a 0.02.
All right, so then now that we've had our base idea and kind of came up with what we wanted to do and chose an airfoil, we need to figure out how we're actually going to implement it into the wind tunnel itself. So the first steps was I came in here and we looked at the current airfoils that we had available to us. Originally, I've seen this one on the table and saw the pressure taps coming out the side, and so looking at the wind tunnel and seeing the opening, that was our original plan. That's why our design is the way it is, and we'll talk about that in a second. But as well as I knew I needed to attach it to the bracket that is currently in the wind tunnel. And I guess I'll touch on that in a second as well. But so once we had the conversations of what our general idea was for how we're going to test and what we were going to test, then we moved into the CAD work.
So our math models, we made 2 separate math models. They're based on the same core base, and the second model just has a winglet. So they're both comprised of 2 main sections, a top half and a bottom half. This was done to ensure that we could ensure the quality of the pressure tubes running through the airfoil. So, yes. So that's the base form, and this is the form with the winglet. The winglet is a 20% height to the cord length. So our cord was 8 inches, our overall span was 9 inches, and so the winglet height was 1.6 inches from that cord, like the center section, so the cord height. And this is a cutaway of the actual like tubings and the pressure taps running through the wing. So as you can see, like by cutting the wing in half, it makes sure that we weren't going to accidentally have filament fill in those sections. Lastly, by looking at the math, and this was something that we kind of did in retrospect, we looked at the frontal areas, and the frontal area of the base form is significantly smaller than the frontal area of the winglet. And this, I think, helps us understand some of the results that we'll go over later. So to summarize, we had a 5-degree angle of attack, a 9-inch wingspan, an 8-inch cord. The base airfoils were identical between the 2 designs. The pressure taps are the same. The bracket is the same. The winglet height was 20% of the cord length, and our overall aspect ratio was 1.25. Now this is very, very low, I will have in mind. So like this specific cord should ideally go on a wing that's like 60 inches long. That's more representative of what you'd see on like real aircraft. And here's some sketches to show you kind of the dimensions and the drafting aspect of this. And there's dimensions for the top. Hand it over to Michael to discuss how we brought this to life.
Yeah, so as I discussed earlier, we got those original ideas from the airfoils that we have here in the lab. Once Alyssa and I CAD'd them and we got them printed was the first step. Similar to everyone else, the printer was slightly too small for our second airfoil with the winglet. But for our first one, it actually worked out perfectly where the print height was just above, the max print height was just above the length of our wings. We were able to print it vertically to make sure everything turned out great. And so we really had no defects on this one, so it didn't